Okay, second video. Now we're going to try to get the data collection piece to happen. So what do we need here? We need a data collector to exist. I am going to add it up here in my imports. I'm going to say, hey Mesa, data collection. I need to import the data collector. And that is going to be able to let me incrementally remember different things as my model is running. So let's go put it into where it needs to go. The model needs to say, great, I have time, I have space, I also have a data collector. Self.dc is my data collector. And my data collector is going to have a dictionary where it talks about what am I collecting. I'm going to collect things called, is something flashing or not? How many things are flashing? Well, to actually put this over here, I would like to write a method down below. Let's write another method down here. This is going to be my method that tells me how many things are flashing. Count flashing. And it's going to bring in the self. So, how many things are currently flashing in the model? I am going to say there are 0. Return that number, but in between, let's go count them. So for each Firefly in self.schedule.agents, this is a great just list of all the people. Remember, I added them up here to my schedule, and now I am walking through all of them and saying, hey, each Firefly, let's ask you a question. If you are flashing, this is the handy method we wrote before, count plus equals 1. Okay, so it's going to return that number. Every time somebody says, hey, data, how many things are flashing? Let's go give it a function up here. Now, to do this, technically, we have to create a lambda function. A lambda function says, I don't really want to call self.flashing right now, or self.count flashing. I am going to say, what is my number? M is going to be the result of self.count flashing. So my dictionary here is going to say flashing is equal to go out and call it whenever you need to. You can keep on calling this and collecting things and putting them under flashing at every time step. Next thing we need to do is say, well, let's collect the data. Self.DataCollector collect from this model. And it'll say, oh, go look for this model and go put things together with this lambda function. And go figure out what's going on here. Okay, I think that'll take care of it for us. Let's compile that. Shrink it down so you can see it a little bit better. Now our Firefly world has a time, space, and data collection. Okay, we're ready to go start testing it. Let's make our Firefly world. Make it 30 by 30. Does that work? Ah, no, because I forgot to rerun the first part. Import everything again. Now, can I make a Firefly world? Yes, so my constructor here worked. I was able to test that right here to know if it worked. Great. Well, let's run the model. Let's see if you can run out for 500 time steps. It worked. Okay, let's get the results. Hey, data collector, get model vars data frame. This is a handy data frame. We love them from pandas, and it tells us at each time step what is the value of that flashing. Notice here, that is what I put in here in my data collector. And the number that's associated with it at that time is self.count flashing. Okay, so here we go. Now I want to plot it. It's going to be helpful to have some other things put together in terms of the time, results, time, let's have that equal a linear space from 0 to the length of results minus 1, length of results. Let's add a new column in here. You can go see it has 2 columns. Perfect. And that makes it so much easier for us to plot. Results. This is my data frame. The aesthetics here in plot 9, x equals time, y equals the flashing column. And I'm going to add a line. Perfect. Okay, this is what happens. Every Firefly started off at a random time, and they are cycling and flashing every 10 time steps. So this graph repeats every 10 time steps. We want to really see that. Let's just do it, say, 30 times. Go through and run the rest of our things. Notice it repeats 3 times this pattern. Whatever the pattern is, whatever gets created, nobody is talking to anybody else, but it is able to repeat every 10 time steps. The same fireflies are flashing. This is good. We haven't done everything, but we have fireflies, and we have a model, and we have a plot to see what's happening here. Okay, let's crank that back up to 500, because now I want to help these fireflies talk to each other. Let's see if we can do that part first. Fireflies, what is happening with your clock? I am running my own clock, and nobody else is influencing it. Let's change that up. I'm going to say, hey, if you're not flashing, let's look around. What is going on in my neighborhood? Maybe I should be flashing because my neighbor is flashing. If I can find a neighbor that's flashing, then let's change my clock and put me at the same exact time that they are. So notice at the beginning here, I am going to be changing my clock to go up by 1. This is the part where it starts to get tricky though. If I'm going to look at my neighbors, I really want to be doing this simultaneously. So it's not like, hey, I looked at a neighbor, but then before they get to look at me, I already changed my clock, and now I'm at a different time step. I want everybody to be doing stuff simultaneously. In Mesa, the way we do that is with 2 step methods. One step gets you prepared, and then the advance method actually moves you along. So if you do a step method, you can look at everybody else and ask what their clock is without them having called step before you and changed their clock. So if everybody's clock is static when you look around, and then when nobody's looking, everybody changes their clock. That's what we want it to look like. So let's do that. Let's just rewrite this code to have another variable. This variable is going to be my underscore next, and it's going to say, hey, what should I be doing next time? My next time should be clock plus 1. But if that's too big, my self.next should be 1. My advance is where I say self.clock equals self.underscore next. Now just to prove that this doesn't change anything yet, it's still the same thing. Because we're not talking to neighbors, we should get exactly the same behavior. There's our regular periodic pattern here. Perfect. So it opens up the possibility though, for before we set our clock to be the next, we look around at everybody else's clock. We don't ever look at anybody else's next. That's one of the reasons we put an underscore in front of this variable, is to remind everybody, don't look here. This is my private data in here. It's easier to do it like this and just have a convention than actually try to do private and public variables here in Python. So we use underscores just to help us remember that we shouldn't really be looking there if we're not part of the self. So self.clock. That's everybody else's piece I want to look at. So let's go get those neighbors. Who are the people in my neighborhood? We've got to talk to the model and go talk to the model's grid. Notice we have a link to our model, self.model. That got set up here in the init. And then we talk to the grid. That's the grid we put everybody inside. Grids are pretty cool. If we look at the Mesa documentation, we can see that a grid has a width and a height, and it has some really cool methods that we want. We want to get the neighbors. Down here, there are two different ways that we can talk to it. We can get the neighbors, which returns to us. Let me zoom in on this page a little bit so everybody can see it. When I say, hey, grid, get neighbors, I give it a position. I give it a Boolean. Do I want the Moore neighborhood or do I want the von Neumann? Do I want to include the center? This is by default false. And do I want the radius to be bigger than 1? It's going to return to me a list of tuples int int. So that's what get neighbors is going to be able to do for us. But if I have something bigger, like a multi-grid, let's find the multi-grid. It is going to do something else. It's going to return to me a list of the things that are there, not just the individual, but it's going to return to me for everybody that's in my neighborhood. If that neighbor is flashing, then I can talk to them. So let's go back and do that here. So let's go get the neighbors from my position and tell it, yes, I want to use the Moore neighborhood. I want to use all 8 cells around me, but not look at myself. So for each one in my neighbors, let's go look. I want to say if n is flashing, let's change my next value. This is where it says I am going to set my value to 2. Why do I want to set it to 2? It's because it assumes that if my neighbor's flashing, they are flashing because they're at time step 1. When they call advance, they're going to go to 2 because they were at 1 and they did a +1 on it. So that's what I want to do. I want to say self.next, put me at the exact same time as my neighbor. Okay, let's see what happens here. See if we broke anything along the way. Ah, look at that. It started off, it did something different, and then it stayed the same. We had some variation from our initial pattern because everybody looked around their neighborhood and got synced up. But we have a 30 by 30 space and we only have 200 fireflies. And so some of these are connected to others and some of them aren't. Some of them will be able to see in their local neighborhood somebody else, but that information won't get propagated across the whole world. So let's make these fireflies move. I want to say after everybody's figured out if they're going to flash or not, we are going to move. Self.move. Now that would be nice if it just existed, but it doesn't. We have to go define it. How are we going to move our self? Okay, so the way we're going to move the self is to look at the possible moves, and then we're going to choose one and then put ourself there. Okay, self, let's go get the possible moves. Next, moves equals self.model.grid.get neighborhood. So up here we got the neighbors. And down here we're getting the neighborhood. Let me go back. I'm a little confused by that documentation I showed you earlier. If I look at the grid here, I don't think this is right. One of the get neighbors is giving me a list. It shouldn't return tuples. It should return a list of agents. And get neighborhood should return a list of tuples. This should return a list of coordinates, right? A list of coordinates are coming back. And this one returns a list of none objects in the neighborhood. Yes, so the documentation down here is correct, but this up here in their link up here is not right. So I was getting really confused. I was telling you the right thing, but I was highlighting the wrong thing. And I was like, that's not right. Okay, so that will need to be updated in Mesa. But for us, we need to say, yes, neighbors gives us back who is there. Neighborhood tells us the position. So if you're following along, that's why I was starting to get a little confused here. So yes, I get a list of agents, and here I want a list of places. Get neighborhood. Where? I want the neighborhood around the position, and I want to use the more neighborhood. And let's go ahead and say I can stay here if I want to. Let's just call that one true as well. Okay, so more neighborhood. Should I include the center of my small grid? Well, now that I have them, let's make a choice here. Use my random generator and say out of next moves. Finally, hey model, grid, I need to move the agent. I placed it, and now this is the way to tell the grid I'm moving somewhere else. Move me to this spot, the spot that I just picked. These are tuples that come back. I picked a random tuple, and then I moved myself to that tuple. Okay, so when I advance, I set my clock, and then I wander around the space. Now, this way, I will be getting information and sharing information with other agents in the world. And hopefully that will help them sync a little better. Let's see what happens with our plot. Now that they move, it takes them a lot longer to run, but oh my goodness, look at this. Because they are moving around, they can share and they can get their time cycles synchronized completely. So the flashing started off down here, pretty much everybody's doing their own thing. But as they moved around, they looked around and saw their neighbors flashing, and they flashed and their neighbors looked at them, and they eventually all got to a spot where they could sync up together. Okay, so two more things I want to do. I want to make this an abstract model to start including different times, like 10, it's a magic number here. How long do they flash? That's a magic number here. I need to fix those up for the rest of the pieces on the exam. And then I need to make the visualization. So 2 more videos after this one will come up next.